Okay, then I would like to introduce the next speaker. We're going to the rural areas, in contrast to the urban areas we have been discussing. Professor Nicola Fohrer is Professor of Hydrology and Water Resources Management at Kiel University since 2003. She is particularly engaged in research in rural areas, not only in Germany, but also, as I read, in China, Russia, and India. So it is a focused view on a worldwide issue. She studied at the agricultural sciences at the Technische Universität of München and graduated at the TU Berlin in 1991. You got a PhD in soil erosion in 1995, and as in Germany, habilitation in 2002. That is for the real science, you need a habilitation. And you worked on water and matter balances. And I looked up some of her background on ResearchGate. That is sort of open system, you all know it, more than 2 million members. And of course, it satisfies curiosity amongst researchers, how well people are doing, how famous they are. She is very well known. She exceeds the 95%, you leave behind yourself 95% of all of us. So you're a very productive scientist. More than almost 4,000 citations and 15,000 reads. I can only dream of that. But what did strike me at the academia net, she mentions about soft skills. She said, I have a daughter, eine Tochter. That's a soft skill. I have two, so I have soft skills as well, I hope, so I experienced. Your presentation is called Multifunctional Landscapes, Assessing the Interconnectedness of Water, Food and Biodiversity. Please take the floor.
Delegates, I'm very honored to have the chance to speak to you today, and I'm very grateful to have the chance to speak about my favorite subject, which is water. I'm a true water person, and thank you for a very kind introduction. I think that being connected to other people, being connected to daughters, makes you a full person and a full scientist, and it balances you well out for the challenges that you are meeting within your projects. So my topic today will be multifunctional landscapes and assessing the interconnectedness of water, food, and biodiversity. We are trained scientists, and usually when we are trained in a very monodisciplinary way. And I think I'm very grateful for the Nexus Forum, which pushed the doors open to the neighboring disciplines. And finally, we are really looking at the interfaces. And we are meeting other experts, and we can throw our expertise together to solve really pressing environmental problems. And to stop optimizing landscapes for one goal only, which challenges, of course, other functions. And I think the Nexus approach is one that is probably able or capable to solve a big issue. When we look at landscapes, they fulfill a lot of functions for us. On one hand, of course, we produce food in landscapes. So agricultural income is very closely connected to food production. Crops are growing in landscapes, but at the same time, drinking water is produced by landscapes. Water seeps into the ground, takes nutrients, takes pesticides with it, so the more intensive agriculture is, the more challenged might be your water resources. So functions influence each other. Rural areas are also places where employment takes place, where you have farmers, where you have other people earning their living. And of course, there are habitats. They are home of biodiversity. Their species live there. They live in the landscape. They live in the watercourses. And of course, if you change landscapes, you impact also the habitat of species. Landscapes also serve for us. When you go on holidays, where do you go? You go to rural areas, you go to landscapes, you are enjoying the landscapes that are there. And of course, we engineers, we change those landscapes, and we change also these functions, landscapes as places where you have recreation. And tourism as well creates income and might be an alternative source for income, helping to conserve other resources in this case. They can be national parks, they can be settlement areas. You showed quite impressively that, of course, many people move to the coast and people start to live in mega cities and rural areas lose a lot of inhabitants. That also changes the rural landscape and that changes also the way of farming. We came from a really family-driven farm business to a real industrial farm business. We have huge farms. We have farm systems that work like industries that are closely connected to biogas production, for example, and energy and farming is more closely linked in the recent years. So how can we get better? How can we be more responsible with all the landscape functions at the same time? Of course, as I'm a trained water person, I wear water glasses, so I see things through the water perspective. But nevertheless, we try to look left and right and get more experts together to assess landscapes in a more multifunctional way. And water resources, I was quite happy to hear from my pre-speaker that you think it's urgent that we spend more money on water and water conservation and also on water sector. So water is greatly affected by multiple pressures. As we farm, we have land use that affects water quality, for example. But of course, we have also a lot of point sources. If cities are growing, sometimes the wastewater systems are not growing in the same speed, so we get in trouble with wastewater impacts. Or we alter and modify the river morphology and thus have a big impact on aquatic habitats. In developing countries, this development sometimes is much faster than in Europe. Europe is let's say, a grown economy, so growth is taking place at a steady pace, but it's more slow. But if you look at China or at India, for example, economies are exploding. Population is growing in a very fast rate. Countries are changing. Sometimes when you travel one year and you travel in the next, you don't recognize the landscapes anymore because the changes are so fast and so dramatic. And of course, as we see that landscapes are having all these functions, if you change one function very strongly, it has impact on all the others. And being monodisciplinary, you are not able to capture the whole picture. And then you might make decisions which might have drawbacks in other landscape functions. So it's time, I think, highly time, to have also the Nexus idea there and make a multi-goal optimization of landscapes. So consider all the goal functions and not only one, and deal with the consequences. So what we do, or what we try to do in many projects, and I will give 3 examples of different projects, we try to have an integrated view on the landscape. We try to see more functions than one. And we try to apply an interdisciplinary modeling framework. Usually we have hydrobiologists or agronomists or water resources managers that deal together, that try to analyze landscapes together. And in the recent approaches, we also try to link the biodiversity, because usually biodiversity has no stakeholder that speaks for them. So sometimes they're overlooked in decisions. So in the process analysis we do, we take the hydrological processes. Wow, this is not working very well. We take the hydrological cycle, of course, which is land use driven, which is landscape driven, which is soil driven. And we try to link it also to the living environment. Also, so what does it do if you change land use? What does it do if you change the management of water resources? What does this do to the aquatic habitats? What does it do to aquatic life? I have brought 3 examples, getting more complex with the examples, and I was also quite happy that you mentioned already the Gorges Dam, which was a huge engineering project in China. And it has, of course, the main purpose was flood protection, which makes very much sense. It's also the energy production, so the Gorges Dam area produces as much as 18 nuclear power plants, so it's quite a lot of energy that is produced. But what does it do to the area? What does it change in the area? So the first example I'm bringing to you is the energy demand-induced land use change, because this was the basic idea. We want energy, so we change the landscape, we make a big reservoir, we have flood production, we have also shipping improved. So what does the case of the Gorges Dam do in the catchments that are connected to the dam? This is a photograph of the dam. It's nearly 2 kilometers long, and it created a reservoir which is about 600 kilometers long, so this is about the distance from Berlin down to Munich nearly. And it creates in the history of the flooding of the dam, of the impoundment, a lot of resettlement and restructuring of the local infrastructure. So we have the resettlement in rural areas because the whole valley bottom was flooded. The inundation level is about 180 meters, so the whole valley bottom is gone. So people started to move cities upwards, hill upwards here. And of course also agriculture moved from the valley bottoms which are flooded now, it moved uphill. And you can see that the uphill areas are very, very steep. And the cropping system itself went from subsidy agriculture, so from really growing the own food, to more to market agriculture. So it moved to orange plantations, and an orange juice plant was built there so that the farmers should have an alternative income source. Well, our working hypothesis in the beginning was that, of course, due to the construction of the dam, we have a big land use change in the neighboring valleys. So you see that agriculture moves hill up, and we had the hypothesis that then, of course, you hit more erosion, and also the hydrological regime changes very much, meaning also the moisture regime around the reservoir changes a lot. The porous pressure in the rocks and in the soil change a lot. So what we observed, or what our group observed also, was an increase in landslides. Of course, beforehand you had a river here with high flow velocities mixing oxygen and so on. And after building the reservoir, you have a 600-kilometer long lake. And of course, the flow velocity was reduced dramatically, and what occurred then was the higher eutrophication, more algal growth, and depletion of oxygen in the reservoir. So we looked into in a study area which is really next to the Three Gorges reservoir. The reservoir is down here. And we took this as a sample case, how land use will change in such a catchment and what kind of impact might this have on different water resources elements. Firstly, we did a field campaign. We started mapping the area, so students went to the area and they took photographs, and we produced maps of the change. So where did agriculture go from originally valley bottom to uphill, and how does agriculture look like? Is it terraced? Is it in a good shape? Is the soil covered? Do people grow orange trees? Do they grow bee cropping systems, or whatever do they do? And we had additionally farmer interviews, so we went to the field, talked to the farmers, those who stayed. About 2 million people were resettled, but there's quite a strong population still in the area, and they have still the traditional farming systems going on, small scale, very typical for China, small scale farming, nearly like horticulture. And we asked them about their management systems, about fertilization, about the crops, how many crops do they grow per year, and so on, to have an idea if the livelihood for them is still functioning, and what kind of consequences does this have for the production on their fields. Additionally, we used remote sensing information to see what kind of large-scale change in land use might there be due to the reservoir building. And you can see the reservoir was started in the 90s, and then the reservoir was inundated. And you can see in the last remote sensing image that here, this is the reservoir. It's up here, and this is the mouth. Here's the Three Gorges Dam. So it's a 600-kilometer reservoir that has built up. When you look at the remote sensing images, though, you see, but there is no big land use change. I see mainly forest and tea, which is true. In the upper areas, there is still a lot of forest, and of course the Chinese government implemented also land use protection strategies. So they tried to, what left is the agriculture here. And what was transformed was basically along the streets, because it was now more accessible, the production of market fruits like orange crops for for juice production. So the system moved from homegrown food to producing for the market, producing orange juice. And of course, the changes were the largest along the main transport pathways, the roads, because of course market fruits have to be transported along the roads and streets. We had the largest changes. So if we looked into the land use change that was initiated by the dam building, we saw that there was a conversion of cropland to orange orchards, and also a conversion of cropland to forest due to conservation policies of the Chinese government. And the land use change was relatively small. If we look now at water balance and sediment balance, we can actually see our hypothesis was just the other way around. We have a lot more sediment entries by erosion, but the analysis showed that there was less erosion now taking place because there was more forest actually, and the orange trees also covered the soil quite well. So we had in the early years quite a lot of sediment, and this was reduced in the later stages of the Three Gorges Dam. And we can see also that we have a change of fast flow components from surface runoff to more groundwater related, so to seepage water, to groundwater infiltration, which is good on the one side because you gain more water in the soil, but which was not so good on the other side because slopes got destabilized and we got more landslides because the whole system got more moist. For the detailed assessment, we looked along the roads and saw that if we look at the direct area of the dam, we can see that alongside the road, the erosion risk and also the risk for landslides increased dramatically, while in the backlands further back, there was a better protection with more forest. So this was a simple land use change induced by reservoir building. Second example, what happens if we add biodiversity? So if you want to know what land use change, what climate change does to an ecosystem, how does it change the water resources, how does it change aquatic biodiversity, which is one of the biodiversity components which is declining the fastest globally. So a second example of a river in China which feeds the Poyang Lake, which is also, I think, the second largest lake in China. And the area is very much prone to climate change impacts. Of course, we try to model the drivers, climate, land use, and river alterations, which we can monitor in the area, and we couple a hydrological model with a hydraulic model to characterize not only water balance components, but also the properties of flow, like flow velocities, flow depths, and so on. And we try to model also sediment balance, sediment transport, because all those, they impact the biological system. They impact the habitat properties of such catchments. And in the end, we feed all these results of the hydrological and hydraulic studies into biological models to see how biodiversity will change. For that, we have a field. In all our projects, we always try to go to the field to really learn how the system is ticking, how is it working, and what are the susceptible factors in the system. So we had information about water quantity, water quality, and management of agricultural areas. And we also collected with the colleagues of hydrobiology, they collected water samples and determined the species that were there. And then we implemented a water balance model and a hydraulic model for the current status, and then fed in climate change data and land use change data for also a scenario analysis. And then we fed all this into species distribution models as a base run, what is there, and as a predicted run, what will be happening in future. The study region is also very typical, like horticultural agriculture in China. This is the Yellow Mountain, so it's a very remote area in pieces. And then, its agriculture is mostly taking place in the valley battens, and it's also a very strongly forested catchment. If you do this kind of interdisciplinary nexus work, I think it's very necessary that you go jointly to the field and that you hear also what other disciplines have to say. So go with the agronomists, go with the hydrobiologists, go with the hydrologist and the hydraulic person, because they will all bring in different information about the landscape. And this is what we did with the interdisciplinary field work, measuring hydraulic input parameters like cross-sections and so on. And the colleagues from hydrobiology, they took water samples and they explained us what kind of species are there and what do these species need for having a good habitat. So do they need sediment, or do they need low flow velocities, high flow velocities, and so on. So we understood quite a few things more about what aquatic biodiversity means. We fed in our field data into the HECRAS model, which is also from the Corps of Engineers, a very useful tool for hydraulic modeling and for floodplain modeling. And we calculated water depth distribution, flow velocity, stream power, and sediment discharge in the area of this catchment. And with the water balance model, we showed which water balance component is dominating. So where do you have fast surface runoff, where do you have infiltration and groundwater recharge, and so on. And we pointed out also the seasonality and the components of the water balance during that time. The hydrobiologists then used this data set which we produced for the current situation, and they said, okay, what's useful for us is, for example, as climate input data, quite a few weather data, so seasonality obviously is a point for these two species. The temperature during monsoon is an important feature, but also flow seasonality, which we can provide as hydrologists, but also landscape features like slope and slope aspect because they influence the sediment balance. So what they calculated then is the species distribution here for a shell and here for a caddisfly for the hydropsyche, and they showed quite nicely where in the catchment, depending on our hydrological factors, would occur these species and how would they change. If we integrate also hydraulic variables in the biodiversity prediction, then the prediction gets even better for these shells. And you can see that the sediment transport from our hydraulic models, the flow depth, flow velocity, and stream power contributed quite nicely to model the occurrence of this Spherium coneum species in the river mouth. So you make the full pathway from land use change, climate change, hydrological change, hydraulic change, down to biodiversity change visible. And I think this is a great way to support decisions, so you can really see how systems respond as a whole. Okay, last example, we're going to cold northern Siberia. Ecosystem service approach is one of the approaches which makes landscape functions visible and also useful for optimization of different goals. So our project aim there was to assess the water-related ecosystem services in the northern Siberian lowlands. You see already one picture here from the field work, which was quite a challenge, but nevertheless it's a very susceptible system. As if you have a temperature rise there, then the snowmelt regime moves. And then, of course, you have a quite different flood regime, and snowmelt and the flood regime after snowmelt is the hydrological event in the year. After that, it stays dry till autumn, and you have to deal with the water you get during snowmelt. That's that. If you can do agriculture with that, it's fine. If it's not enough, if you don't store it well enough, then you will not have a crop. So a very, very susceptible system in terms of climate change. Ecosystem services, I think everybody is familiar with that concept. Very, very fast we deal with the provisioning services, which would basically be our food, whatever food production, agriculture is taking place in the area. Then we have the regulating services, which came into discussion when we discussed carbon storage, for example, climate change and carbon storage, water storage. So landscapes are a great transformer of matter transport and also of water transport. And of course also cultural services, so they are landscapes which you want to visit, or they have special features which make tourism, for example, a possibility. Again, we set up our models. We try to assess in the field study first more system knowledge. How does the system work in terms of hydrology? And we ran global change scenarios and saw how agricultural production, for example, would change, or what kind of features would be possible with rising temperatures. And then we also analyzed the ecosystem services as a basis for local decision making. So if you change agriculture, how does it change the water-related services in the area? And we had three basins in the area. We had the Pishma, which is a large river in the Oblast Tyumen. We had the Vagai and Loktinka, so on different scales. This is the lowlands of Siberia. This is also the grain belt. It's near to the Kazakhstan border. So in the south it's quite warm. In the north it's getting very, very cold. And yeah, we had the interdisciplinary field work again. We had the soil people assessing the soils, the soil salinity, water quality, and hydrology. As there was the breakdown of the Soviet Union, there were very few hydrological data available, so we photocopied whatever we got and we measured quite a few things. And of course, the system analysis showed quite clearly that a huge seasonal variability takes place, which is affected by climate change, that we have a snowmelt-driven flood event in spring, and it's the event in the year, so you see basically only one event, and that's the snowmelt event here, also in pictures, everything frozen. This is the course of basically 2 weeks, and 2 weeks later everything's already flowing, so a very fast flow peak. And then you see also in the rest of the year you don't get any further water, so rainfall basically stays in the soil, it's stored and doesn't create any runoff. And a lot of the system functions with groundwater influence. So if you see the groundwater, fast groundwater flow components, they are the dominating flow components in that area. Coming up with the ecosystem services, we discussed with the ecosystem people what kind of indicators would be suitable. And this is a landscape where you have a lot of depressions, so it retains water quite nicely. And this water retention is needed because otherwise you will not have enough water in the fall to have really a harvest. So the water is needed in the soil. So one service we looked at was the water flow regulation. And the darker the green, the more important the flow regulation becomes. And you see in April, May, lots of the soil is still frozen, so there is no retention in the soil because it's frozen. So the water flow regulation is not that prominent, but in July, when water gets scarce, then it's the dominating factor for agricultural production. So if you keep your snow melt in the soils and you are able to store it in the depressions and in the peatlands, then you will have still water in August or in July to grow your crops completely. So this is why it's important to show the functions of a landscape and then base decisions as a whole on it. So what can we do? What is well understood for my conclusions? I think modeling the impact of land use change, climate change on water balance components, this is something we can do. This is basic tools for hydrologists. This is what we teach our students already in classes. Even if we have data scarcity, we get a good system understanding. And even if we have non-stationary conditions like the big changes of the Gorges Dam and so on, we are well aware how it works and how it functions. Where do we make progress? I think we make progress due to the Nexus initiative also to link hydrology, hydraulics, aquatic biodiversity, and how does it function under global change. We're making big progress there, and hopefully this is also then a bridge for decision-making to have more freedom in decision and to see really the consequences of building a dam or of having flood protection measures. Ecosystem services are also a valuable approach to show what kind of multifunctionality landscapes have and to make them operational so that you can really base decisions and see how land use functions change. Where we still need to make progress, there are quite a few things. I tried to squeeze some on one slide. I think it's high time to see that landscapes are multifunctional. They have a lot of different functions. And if you change one, it will have consequences for the others. And we have to start to make really multi-goal optimizations and not just make a flood protection without considering other consequences or taking maximum agricultural yield and not considering the consequences for water quality, for example. This, at the end, is more cost-intensive for a society if you don't consider the other consequences. And it should be a stakeholder-driven process. So take the local experts, take the people who have a say in what is decided, and try to implement or try to get them engaged early on. Thank you very much for your kind attention.
Thank you very much, Professor Fohrer. There's room for 1 or 2 questions. Please raise your hand. Mr. Bogardi, I believe.
Very much in the spirit of Nexus, and also seeing one of your first hexagons showing natural parks, and it was a lot of rapeseed fields. It reminded me, how does this multifunctional landscape may change or influence if we take the water, energy, food security nexus and using the landscape more and more to provide energy?
Mm-hmm. Actually, the energy production by crops is one of the swords with 2 sides. Now, on one hand, of course, we have a sustainable way of a regrowing way of creating energy, but on the other hand, it's a big challenge for water resources and especially for water quality. In my federal state, we have lost lots of areas where now agricultural crops are again produced for biofuels, and in this case, it has a dramatic impact on water quality, on nitrate pollution, for example. On the other hand, it's also a competition for areas for food. So also there, it's a sword with 2 sides. So again, it has to be a multifunctional optimization and not only a one goal. We want energy decision. So we want energy, we want it sustainable, but we want clear water and we want food for the people. So these are the questions which you have to answer if you implement a new direction, I think.
Okay. Very interesting, your talk. You mentioned for the Siberia study the agricultural water management or agriculture management scenarios, and particularly keeping water in the soil, because there is no, very interesting. I would like to ask you, how great is the diversity of soils? Because different soils have a quite different water holding capacity.
Oh yes, definitely.
And you also have the rooting patterns that are very important,
definitely.
also because of the remaining ice, probably, permafrost and so on and so forth. How do these soil differences play a role in the overall analysis?
Yeah, I'm quite happy to have one of my great teachers in soil science and especially plant nutrition asking that question. So it's a big challenge, of course. The soils are very, very diverse. The rooting depth depends very much on how fast the ice goes out of the soil, because the plants follow. And the plants follow, of course, only if there is no water in the soil impeding root growth. And of course, storing it depends very much on the carbon content of the soils. No? And if you drain the wetlands, for example, then of course you lose a lot of carbon and you lose a lot of possibilities to store water. So it's a very, very, very susceptible system and highly complex. What we did is just to do a large-scale rough sump analysis, but I agree completely that of course you should look into the grain size distribution, into the carbon content, into the defreezing of the soil depth, allowing to store water. So of course, if we have the rough analysis we see now, in July it's a critical time of water storage, so we should look then on the variability of soils and go into more detail for sure. Mm-hmm.
Okay, thank you very much. I have a small question to conclude, if I may. Are we institutionally well enough equipped to absorb all this sort of transdisciplinary almost information we have?
I'm not sure. I'm not sure if I'm the right person to answer. I think we're making a good step when we start at university to work more problem-oriented and stop doing really only disciplinary work. I think then we might have a future generation which thinks it's completely normal to sit together with a person from groundwater, from hydrobiology, from economics, from agricultural sciences. If we manage this on a first educational level, I think the next generation will have to solve bigger problems than we do, and they might be better prepared than we are.
Okay, thank you very much, Professor Fohrer, and also thank you very much, Dr. Della Priscoli. Please give him a big applause.